right, so we're up to the official time. This is CNET 127, Exploit Development. And what we're going to do today is Chapter 2 here, which is going to be Stack Overflows on Linux. And then I'll demonstrate some of the command injection projects and such. But the Stack Overflows is very interesting stuff. And let's look at it. I've got some slides, but it's mostly going to be demos. So we're going to talk about how C stores buffers, and then how you can overflow those buffers, because C does not protect you from that. There's the whole problem with C. So the simplest attack is an information disclosure attack, where you read data that was not intentionally revealed to you by the developer. Then we'll use a debugger and go to a segmentation fault, which causes a program to crash, and we'll look at the stack and how it's used, and a stack buffer overflow. And this is the heart of the whole course. This is the #1 vulnerability that caused generations of malware. Most Windows XP malware was stack buffer overflow exploits, and a lot of it still is, and the other vulnerabilities are variations on this one. So this is the most important thing to understand in the course. It all came from Aleph Null, who in 1996 published a tutorial in Frack magazine which exposed this to the world. Previously, it was sort of a secret black hat technique. But he explained it in this article in a way that a whole generation of security students were able to understand it, and that is the basic exploit that's used to take over machines. Now, if you're going to use a 64-bit Debian machine, which is what I like to use, then if you want to compile 32-bit code, you have to install Build Essential, GCC, Multilib, and GDB, so you can compile 32-bit code on a 64-bit machine. And the only reason to compile 32-bit code is because it's easier to understand, and it's where I like to start. All these techniques work just as well on 64-bit and on ARM. 32 and 64-bit, and I'll demonstrate the ARM version later. So here's the simplest exploit. You make a simple program here that declares an array with 5 elements and puts in 1, 2, 3, 4, 5, and then you print array number 5. And here's one of the many irritating things about C. C starts counting at 0. So this is element 0, 1, 2, 3, and 4. So array element number 5 is not part of this array. You'd have to have 6 elements in the array for this to work, but C is too stupid to notice this is a flaw. It will just, when you print an array bracket number, it will just start at the location of the array and add enough bytes to count to this number and print out what's there. It will not go back and check to see if you actually initialized that much of the array. If you have GDB, will those commands interfere with it? No, it won't, ACRN. All it will tell you is that it's already installed, or it might update it to the latest version, but it won't do any harm. Good? So let's take a look at this one. Let me get my Intel-based machine, which is in the cloud. So I got to go here. This is in my private cloud at home, running on a server. And because I'm using an M1 ARM here, I don't have, what is this garbage? That's the right thing. Just a moment. Oh, that's the wrong password.
Are you still using LastPass?
What's that?
Are you still using LastPass?
Yes, I am still using LastPass.
They just got hacked again.
Yes, they did just get hacked again. Yeah, I know, and I haven't done anything about it yet.
They say expose the users.
Yes, yeah, I know. So maybe I'll move off them, but I haven't been motivated to bother yet. Yeah, so here's my Debian machine, and there's my console. All right, so this is an Intel-based Debian machine in my private cloud, and let me close that tab. All right, and I think I'll make this a little higher. Well, maybe I can't. All right. I mean, I can make this a little higher this way. All right, that'll do it. Just think it'll be easier to see. All right, clear. All right, so if I do ls, I've got a variety of these programs here. So if I cat, the first one is ch2a.c, and there it is. And maybe I can make that a little bigger. Yeah, all right. And a little higher again. There we are. So this is the program I just described. And to compile it, you do gcc Minus G includes debugging signals, which is a good thing. Minus M32 makes 32-bit code. You put the output file in ch2a. This is the Linux convention. The executable program has no extension. And you feed in the input there. And so that will do it. And now you see now I have a file called ch2a. If I use the file command to see what it is, this will tell me it is the 32-bit Linux executable, which is ELF, executable link format. This is the Linux format. So I've made a 32-bit executable program here. And let me run it. It's called ch2a. So if I run ch2a, it prints this strange large number, minus 308,000. And if I remember the source code, is confusing because I only put in 1, 2, 3, 4, 5, but I printed an element that was off the end of the array. So that is the information disclosure vulnerability here. This reveals something that the developer did not intend for me to see, some value that is just hanging out there. So let's use the debugger and find out what's going on here. GDB is the main debugger you use on Linux. It's very powerful, but it's command line only and can be confusing. I started with the minus Q switch to avoid having an irritating banner. And then I just put in the executable ch2a, and this will launch the debugger. Now, there's a few things you can do here. Since I compiled it with the minus G switch, it connected the source code to the executable. So you can do source code debugging. So if I just type list, it will show me the C source code. I do not need to read assembly code to debug this thing. So if I want to see, let me go back to my slides and see what my plan was. All right. Now I want to put a break at line 6 and run and then look at the array. All right. So here's line 6. Here I've defined the array. Here I'm about to print it. I'm going to put a break before this line, so it'll run that far and then stop. So that's break 6. Now I run. It hits the breakpoint. Now I can examine that variable, which is &array. That is the dereference, so it will show me the data pointed to by the array variable. And there, it showed me the first value there. That's the 1 I put in there. If I want to see more of them, it's x/8x. &array. To see 8 of them. So now I see here, let's see if I can make my thing fit on the screen a little better. And I wonder if I can make it wider. I may not be able to. Looks like I can't. So I'll make this font a little bit smaller. Make this easier to read. There we are. So you can see 1, 2, 3, 4, and they are 32-bit words, so it takes 4 bytes for each value. Here's the 5, and there's the next value, this FF, which is a large negative number. Negative number starts with a 1. So when I printed out array number 5, which I can do by continuing, you see this -1, 1, 4, 5, 6, that's this number. So what I'm seeing a value which is used for some other purpose than storing this array, some value that I shouldn't be able to see. And the debugger helps you see, this is the simplest kind of memory corruption. I haven't put something bad in memory, but I am accessing memory that I shouldn't be able to access and printing it out for the user when that was not what should be possible. So that's the simplest vulnerability. And so now you've seen GDB, and here's a few commands we used: list to show source code, run to execute a program, break to put in a breakpoint, and X to examine memory. You're only going to need to learn about 10 GDB commands. There are hundreds, but we're only going to use about 10 in this course because we only need to do simple things in the debugger. So now we'll move up to a denial of service attack, which is going to be reading past the end of an array. So this is ch2b. Let me just go to back to my live demo. All right, so let's get out of the debugger and clear and cat ch2b.c. So this one, again, I define an array of 5, and now I just start printing array at element I, the address of the array element, and then the data of the array element, and I'm going to skip forward by 64s. So I'm going to go up to 10,000 past it. So this is going to print a whole bunch of arrays. The array only reserved space for 5 elements, but I'm going to jump forward by 64, 128, 196, 256 to read way off the end of the array. So if I run this one, ch2b, see, it prints a whole lot of values. Here's the array starts at this address, then it goes forward by 256 bytes, which changes this letter here, because each element is 4 bytes long, and I'm jumping forward by 64s. So that's 256, so C, D, E, F, 0, 1, 2. I'm jumping forward by just incrementing the third place from the right. And it grows and grows and grows, and then hits a segmentation fault. So it grows up to this value, and when it tries to go from 9F up to A0, it fails. And we can see why. Let me just check my slides and make sure I stay on track. By the way, this is a format string, %x. That means print this value in hexadecimal, is what we're seeing there. And I think I better close that door again. They're being noisy out there again. Anyway, so now we can observe address space layout randomization. That's one fun thing. So if I run this program, ch2b, notice this time it ended at 5F78. Next time I run it, it's at 8F78. Next time I run it, it's at 9F68. It's different every time. This is a very common security feature now. Every time you run a program, it randomly relocates to a different memory location, so you don't know where the program is running. This is an attempt to stop buffer overflow attacks. Now we can turn that off. I saved the command here. If I can't disable ASLR, this is the command that will turn that off. Randomize VA space, procsys kernel. If I put 0 in there, it will turn it off. And I can do that with sudo bash this thing, disable. That will turn it off. So now, if I run that program a few times, it ends at DF38. And if I run it again, it's DF38. And if I run it again, it's DF38. I've turned off this feature, so now programs do not randomize. It just puts them in the next available memory, and it doesn't change. Every time I run it, it's the same. So that's one thing to make our life easier. We turn that off. And now we can debug it and see why where it crashes and see why it crashes at that location. So if I might as well clear, and then I use GDB -Q to get rid of the banner, and I look at ch2b. Okay, now, if I list it, I can see the source code. Now, if I run it now, it's going to print down to this address, FFFFDF08. And if I want to know why it crashed when it tried to move forward again to E008, I can tell that by seeing the memory modules allocated for this program. And that's info proc mappings is the command to see that. And you will see that there is, let me go back and look at that address. It was, okay, it crashed when it tried to go to FFFFE008. So FFFFE is off the end of something. And, FFFF, here we are. This is the stack at the bottom. The stack starts at D1000 and it goes to E1000. And it's when we tried to increment to E00 something else, that's when we hit the end. So this is the reason it crashed. The stack only allocated this much room, and I jumped forward until I went off the end. So that's why it gave that error message. Let's run it again. You'll see the error message was segmentation fault. You have exceeded the allowable memory range in the memory segment that's reserved for this program to use. This is a simple vulnerability, and it is, neither way, not considered an exploitable one. Just running off the end of a memory region, it's very hard to take over the machine with that kind of vulnerability. This is a denial of service flaw, but it is not an exploitable one. You cannot easily turn this into one that will take control of the machine. All right, so that's the memory map showing where it ends, and that's how a denial of service attack works. This is the most common flaw you'll find, and these ones are not very interesting because they don't give you the opportunity to take over the machine. So let's look at the stack. Now the stack works like this. You have the ESP points to the top of the current stack frame, and the EBP points to the bottom of the current stack frame. You can push things onto the stack. That makes it bigger. It puts them on the top. Pop takes things off the top of the stack. And the way it's normally used is not with simple pushes and pops, but with calling functions and returns. So EBP is how you calculate an address on the stack. You have the EBP plus 10. That will move 10 hexadecimal, which is 16, bytes from the bottom of the current stack frame. This is the kind of address you will see to refer to local variables on the stack. So, functions. The purpose of the stack is to make it more efficient to use functions. So when you call a function, it first has to stop processing the calling routine, save its current state, transfer control to the function you called, process the instructions there. Then when the function exits, it has to restore the state of the calling function and set the instruction pointer back to the calling function so it resumes execution of the calling function. And this process where you exit a subroutine and go back to the calling function is the vulnerable spot where the instruction pointer is controlled by data that you might have been able to overwrite in the function. That's the stack buffer overflow exploit. So here's after a function has been called, you have variables stored here, and then you may have another variable stored up here like an array, and at the end of the stored variables is the stored EBP, the base pointer, and the return value. And if you're able to overwrite the limit of this array and change those values, then when it tries to return, it goes to the wrong address, an address of your choosing, and that's how you take control of the machine. So, that's the game here. All right, so when a function starts, it runs a prologue, creating the new stack frame, pushing the old EBP onto the stack to recover later. It then copies ESP into EBP, setting a new base at the top of the previous stack frame, and then it calculates the size of local variables and subtracts that from ESP to make ESP below EBP again to allocate space for another stack frame. And we're going to see this again with a simple example. Let me go here, and this is CH2C. So if I clear again and look at ch2c.c, all right, so here I have a function called f that just defines an array with 5 elements, and here I have a main routine that calls the function called f. And it has parameters a and b, but I'm not using them. And then it prints its return from function. This is just a simple case. So I've compiled that. So if you run this, we're due to 5, all right, ch2c, all right. So it runs, it does this, it returns from the function, nothing is exciting. The interesting thing is to look at it in the debugger. So you use -g and then ch2c. All right. -q for quiet. All right. Now I can do a list, and I would like to look at the stack in various cases here. And let me check my slides to stay on track here. I want to break 10 and 6. Okay. So I'm going to break at line 10 before I call the function, and then I'm going to break at line 6 before I return from the function. So break at line 10 and break at line 6. Now, if I run this, it breaks in the main routine. Now I can look at the stack frames. You do that with info registers. This prints out the registers, which are the memory locations inside the processor. You see them all, and the only ones we care about right now are ESP and EBP. So the current stack frame in the calling function goes from 320 to 328. Now if I continue, I'm going to go into the subroutine and stop inside the function f. And now, remember stack frame used to be from 320 to 328, but if I info registers again, now it is 2F0 to 310. So another stack frame has been built on top of the old one at lower addresses, and this is going to be used by the subroutine. That's the point. All the information for the calling routine are up here at 320 and such, still waiting when I return to it. The new stack frame on top is being used by the current function, and when I return, this memory will be freed again. So, that's the game there, all right. And now we can examine the stack frame, and let's do that. So in the subroutine, the stack goes from 2F0 to 310. You can examine it with x20x $ESP. That will print 20 hexadecimal words starting at the stack pointer. And remember, the base pointer is 310. So the base pointer is here. The 32-bit word beginning at address 310, that is the stack frame being used by this subroutine. These are the temporary memory locations used by it, and this is the return pointer. That is the address of the instruction it will go to after it's done. So if I were able to overwrite this array and change that value, I could take control of the machine, and that's what we're going to do. All right. And here, now we can look at the calling function in the main function. So we can disassemble main. All right. And here is the, somewhere in here it's going to call, yep, here it is, calling F. This is the line that calls F. It has an address and there's the name of the function. So when you call a function in assembly code, remember it called it with two parameters. If let's go look at the slide where you have the source code up here, there. I called function 1, 2 to go into these variables, A and B. So you push the 2 and the 1 onto the stack, and then you call. That's how it works. When you call a function, you put the parameters on the stack and then call the function. That's what a function call looks like in assembler. All right. Now, if we look in the function, we're going to see the prologue that set up the stack frame. So let's get out of this and then disassemble F. All right, and this pointer indicates this is the current instruction we're on because we've run the program and stopped before it returns. So when you enter the program, here's the prologue. You push the old base pointer onto the stack to remember it for later. Then you move EBP into ESP, starting ESP into EBP. For this, you take the top of the old stack and put it at the bottom of the new stack frame. Now you're going to subtract 20 from ESP. So this is where it had to know how many local variables there are. And it decided that 20 hexadecimal bytes, 32 bytes, is enough for all the local variables. So these right here are the prologue of this function. This is the stuff that set up the new stack frame and saved the old base pointer so it can return correctly. That's the prologue. You always have a prologue like this at the start of every function. Then you do the activities in your function. In this case, it's just storing 1, 2, 3, 4, and 5 in locations on the stack, which is that local variable. And then we're going to return. So it's going to leave and return down here. And that's going to return, going to the pointer, which will restore the base pointer from the value you saved here and go to the next byte, which is the return value that was placed there by the calling function. So that's how the new stack frame is created and how it's used. All right. Can you switch it to Intel syntax? It is possible to do that. It's a good, let's take a look at that. It can be done. I forget the command, but I can find it in Google. So let's see if I can figure out how to get a browser window that isn't tied up doing nonsense. There we are. GDB switch to Intel syntax. Set disassembly flavor Intel, I think. Let's try that. It's here. Okay, set disassembly flavor, yep, Intel. I think that's it. Now if I disassemble, yep, there it is. It has the capital letters and it's going the other way. Now the 01 goes here. Yeah, I'm glad you pointed out. Just might as well take a look at this since we talked about it. This is the Intel version of this command. Put 1 in EBP minus 14. And this is the AT&T version of that. Put 1 in EBP minus 14. And you see there's a few differences. This has a letter at the end, which I think tells you how many bytes to move. And it expresses this in this format, minus 14 parentheses EBP, whereas the other one puts EBP minus 14. So good, it's good to see. And for Linux, you usually use the other one for default, and that would be AT&T, which I guess is probably AT&T, yeah. So now it should be back to the usual for Linux. Yep, good. Thanks for bringing that up. That's a good thing to check out here while we've got it all set to go. All right, so that's what the prologue does. And there's the saved return address. We saw that. And by the way, let's check and make sure it's right. So here I am in the calling routine. I'm at this instruction. So if I look at the stack frame right now, if I do info registers, the stack goes from 2F0 to 310. And if I look at the contents of the stack with the X20X ESP, 310 is here. So that is the current stack frame, and this is the return pointer, 56, 55, 61, F2. Now, we can see if that's right. If we disassemble main, we can see the instructions in main. And remember, the current pointer points to 1F2. And right here is 1F2. So we called it here, and when it returns, it will go to this instruction to presume where it left off. So that's the point. That's what the return pointer should do. You remember where you left off. When you're done doing the function, you return here. That's what that number is. So that's the normal function of a properly executed function call and return. And what we're going to do is hack it and break it so that that function does something other than what the developer intended. So now we're going to do a stack buffer overflow exploit. So we need a function that will let us put in data to change the stack, and that's what we have here. So let me get out of here with quit, and then clear, and look at the next one, which is ch2d.c. All right, so now I have a main function which calls user input and returns. And I have a user input function which defines a 30-character buffer and then uses the getS function to read characters from the keyboard, which will read any number of characters. There's no limit. And then I print the buffer. And the point is, I could get more than 30 characters from the user, and then I would exceed this buffer, and that's the buffer overflow vulnerability. Now, by the way, I might as well compile this so you can see this. If I compile it the same way I've been doing it, to make 32-bit code and put the output in ch2d and take the input from ch2d.c, it is going to warn me that in the first place, I didn't define what gets is, but what's even worse, this is the warning: the gets function is dangerous and should not be used. This is the classic buffer overflow exploit that led to all the viruses in Windows XP and everything. Everyone knows C will let you do it, but they'll warn you. You really shouldn't be using this function. This is one of about 10 related functions that take unlimited amounts of data from somewhere and put it in something that might overrun the buffer. However, it didn't stop me, and it will run. So I can run this program, ch2d, and ask me for some data, and I can put in, say, AAAA. And then it works. It just prints out AAA. If the input is not too long, if it fits in 30 bytes, there won't be any problems. Let's put in something longer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is fuzzing. You put in different data, trying to make it crash. And what I'm going to do is put in 50 bytes. There, 5 A's, 10 B's, 10 C's, 10 A, B, C, E, that's 50 characters, 10 times each of the first 5 letters, and now I get a segmentation fault. So I've caused a crash. I now have a denial of service attack. This input has caused the program to crash. I want to improve that, so let's analyze it in GDB. GDB minus Q on ch2d. And by the way, I'm going to put that string in the clipboard so I don't have to type it again. Copy, all right. I'm going to run this. Okay, now first I'm going to run without the overflow. So first I'm going to list and put a breakpoint in. So if I list, here's the user input, here's where the buffer overflow happens. It reads data into that buffer, which might be too big. So I would like to see the condition of the stack after that overflow. So I'm going to put a breakpoint here at line 7. All right, so now I'm going to run it. And now I'm going to give it, it's asking me for data. So I put in AA and press enter. Then it hits the breakpoint. Now I can look and see what has happened. Info registers shows me that the current stack frame goes from 300 to 328. Okay, and I can look at the data that's stored there with X20X, ESP, and 328 is here. It's 320, 324, 328, 320C. And when it says 328, it means you start at the byte 328 and you include the next 3 bytes to make a 32-bit word. So that is the current stack frame. And this is the return pointer right there, which will be the address to resume execution at. And in here, you see 4141, 4141. That's the 4 A's I put in. A capital A is 41. That's why you usually put in capital A's, because it's easy to spot in hexadecimal. So there are the 4 A's I put in, which didn't overflow the variable. So I'm going to run it again. And now I'm going to put in the contents of my clipboard, which is 50 characters long. And now I'm going to look at the registers again. Now, I put in a lot more data, but the stack frame did not get bigger. It's 300 to 328, and this is the flaw of C. In a memory-safe language like JavaScript or Rust, when you put in more data, it will make the stack bigger. So there's room for that data. But C is too stupid to do that. C determined the size of that buffer at compile time, and if you put in more data at runtime, it does not have the ability to resize the buffer. So the buffer only has room for 30 bytes, but I put in 50, and that's going to cause the problem. So now if I examine the stack here, remember it ends at 328. 328 is here. And you see the 41s are A's, the 42s are B's, the 43s are C's, here's the D's, and here's the last D's and the first 2 E's. Here's a bunch of E's. A, B, C, D, E. These are F's. The 45s are F's. Here's a bunch of F's hitting the return pointer. This value here is the return pointer, and I've filled it with garbage, 45, 45, 45, 45. So if I continue, it's going to crash, and this is what it's telling you. The instruction pointer now contains this value, 45, 45, 45, 45, and you can also see it with info registers. The instruction pointer is here, EIP, and it contains that value, 45, 45, 45, 45. Now, you might wonder why that made it crash, and the answer, of course, is that that address is not reserved for use by this program. If I look at info proc mapping, you'll see the only memory locations reserved for this program start at 56, and then they go up, F7 and FF. So I'm not allowed to use the address 45, 45, 45, 45. It's not reserved for the use of this program, so it will crash. So that's the basic essence of a buffer overflow attack. Letting me put in more data than I should enabled me to change the return pointer, and now the code will move to the wrong address, and therefore I can control the box. All right. And so we've used these GDB commands, and you should get used to them. You're going to use them all through the course, at least until we get to Windows, where you have different debugger. But all our Linux exploits are going to use this. List to show the source code, run to execute the program, break to insert a breakpoint, X to examine memory, too many S's. All right. Disassemble will show the assembly code. Continue will resume execution after a breakpoint. Info registers will show you the registers like ESP and EBP. And info proc mapping will show you the memory map, which shows you all the memory regions that are reserved for use by this program. So that's the 32-bit version of this. And let's try some cahoots, and then I'll show you the ARM version. So let me find a browser I can run the cahoots in. Here we go. All right. How do you enter the wrong address EBP to take over the overflow? The EBP is actually not the main thing. What you do is you put a return pointer which goes into the EIP, and that's the instruction pointer. So you can just change the address of the next command to be instructed to any address you want. And then you just have to find an address that will do what you want. The easiest one being to point to an address of code you have injected. So we'll do that in future class. We'll go through the whole thing. And so we're up to chapter 2 here. This is right. And I appreciate some students answering questions about the quizzes there. That's good. All right, good. I'm ready to record this. All right. And there's 27 people online and 2 in the room, so we're probably going to end up with more than 14. I'll wait a few more seconds for people to join. All right. Well, maybe 14 is all we're going to get. All right. All right, so what language causes buffer overflow vulnerabilities? C, of course, and it's relative, C sharp, C plus, and all that jazz. C is like a sports car. Code is really fast and really small, but it's really dangerous. It does not have any of the security features that would slow it down. It's almost like writing assembly code. You're just directly controlling the machine, and that means all the security is the responsibility of the developer. And in practice, we have discovered that most developers do not have the skill to write secure C code. All right. And I see a question about 123. We will not know who's allowed to add 123 until Saturday. There's some time to consider the options. On Saturday, I guess we'll have the final list of who's allowed to add. All right, what memory section is simplest to exploit? The stack, as we said, the simplest exploit is the stack buffer overflow because the stack has a return pointer, so you can easily control the instruction pointer. If you attack other regions of memory, there are memory corruption attacks, but they're more difficult because you don't have direct control of the instruction pointer. And we'll do those also later. All right, in this command, what is %x? What do you call that? That is called a format string. That determines what format to print something in, and it sounds really unimportant, but we're going to find out it's extremely important. You can take over a machine through the format string, and we'll be doing that in a few weeks. All right, what register contains the address of the next instruction to be executed? That is the EIP. The instruction pointer points to the next command that's going to be executed. All right. No, the format string is not the percent. The format string is the percent followed by a letter, like %n, %x, %d. That's what's called the format string. The percent is just a special character to indicate that the next character describes what type of data to print, like X for hexadecimal or D for decimal. And I see Francisco asking about adding 123. The best thing is come to the, well, that's a good question. I'll let you know. Just come to one of my sessions next week and I'll let you know how things are going. I don't think you can add your name to a list because the waiting list is already full. So I expect people that are not on the waiting list will not be able to get in, but that decision won't be made until Saturday. It's up to Liz. She's the main person running it, so she'll let me know. And I'll let you know after she tells me. I guess I'll know Monday night in my class. I'll be able to answer these questions. All right. All right, so what register contains the bottom of the current stack frame? That's EBP, the base pointer. That is the base of the current stack frame. All right, what GDB command shows you the contents of the stack frame? Yep, good. It's a very good question, Francisco. I wish I had a better answer for you, but I will have an answer by Monday. All right, so this is the one. Examine some data at the stack pointer. And of course, you could choose a different number, but for the simple programs I'm using, 20 bytes is enough to see what we need to see. But this will examine some data, and this X here tells it to print it out in hexadecimal format. You could print it out in other formats, but usually hexadecimal is the best format for us. And what GDB command shows C source code? And that's list. Good. All right. Let me record these winners, and then I see a request to go over some slides, which is fine. Okay, we've got Woot and Takumi. And Hunt. Good. All right, so those are the winners. And let's just take a look at the slides, because you said you're confused about buffer overflow, and I understand that is it's a real important issue. So here is a buffer overflow. You have code which only has room for 30. Percent is a special character. And when you put a percent in a format string, it means that there are a couple special characters used in C. Percent means that the next character will tell you what type of data to print. And a backslash means that this has a special significance. So a backslash n is a carriage return. And a %s means print it in string format. That's all. There's a couple of special characters that change the meaning of the next character. So that's what this print does. It will print the contents of this variable as a string followed by a carriage return. And so here is the subroutine that has room for 30 bytes, character variables, and then it gets more. So if you put in more than 30, there'll be a buffer overrun. That's the point of this. And so that means here, when I put in this 50 bytes, it filled all this memory region and it exceeded the limit of the stack frame and it overwrote the return pointer. So now it tried to return to an address which came from the characters I put in. So I've gained control of the machine. Now I've used sloppy attack that just caused it to crash, but it did take some of my data and misinterpret it as an address to control the processor. So just by putting in text data, I was able to take control of the processor. Which hypervisor platforms do you prefer to learn? Overflow, Proxmox, or VM Player, an ARM board? They're all the same, really. The hypervisors don't matter. Anything that works well for you. And it's good that you mentioned that. I'm going to make a separate video now of the ARM version of this. Let me stop this video and make another one.